The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let me just say our next topic, moving really toward machine learning, would be the last section of Chapter 6 about stochastic gradient descent. I think Professor Sra from computer science if he's able, he will take the class Friday and tell us about SGDs, stochastic gradient descent, critical algorithm. I mean, at a quick look, stochastic gradient descent does smaller batches at a time, so it's computationally faster than pure gradient descent. But also, stochastic gradient descent is able to solve probabilistic problems where you're trying to minimize an expected value instead of a function. Anyway, it's an important thing. Actually, there's a lecture at 2 o'clock in neuroscience about the gradient descent algorithms, and then Professor Boyd is speaking here at 4:30 this afternoon. It's overwhelming. So I'm going to talk today about several topics that are specific parts of optimization. Linear programming is a very famous part of optimization. I don't know if you've met it. I think it's worth knowing what the inputs are and what's the key fact about linear programming, and of course also what are the algorithms. That's usually what we want to know. What's the problem? What are the results, the mathematical results, and what are the computational tools? Yeah, so that's a very established. Max flow min cut is one specific linear programming that I think maybe would serve as the best example. And then two-person games. Have you met those? So would you know what the rules are in a two-person zero-sum game? Those are in game theory, those are the ones that are clear, everything's well established there. And in fact, they're equivalent to linear programs. So that's why those two are coming in today. And then the key fact about two-person games and about linear programming is duality. So if there's any word on that board, it's the one in capital letters that has math content. Okay, I'm just going to start with linear programming and then move on. Okay, so what's a linear programming? Linear program. We're optimizing a linear cost function. So we're minimizing the cost, C transpose X. So that vector X is the unknown that we're looking for, and this vector C is the cost vector. So that is C1x1 plus Cnxn. So you can see why it's called linear programming. The cost is linear. The constraints are also linear. So the constraints on X are a set of linear equations. Of course, I'm not thinking of A as being a square invertible matrix. No way. If it were, that would tell us what X had to be, and our problem would be over. We have n unknowns. This is n by n, of course. X is n by 1. That's our unknown vector. And I'm thinking that m would be smaller than n. But we do have constraints, and now comes the thing that makes linear programming not actually linear. And that's the constraint X greater or equal to 0. And I've written that as a vector, but that means x1 greater or equal to 0 onto xn greater or equal to 0. So it's a vector inequality. Okay, so we have a minimizing a very simple function with pretty straightforward constraints, but inequality constraints. So the set of these two together are the constraints that, and it's in linear algebra, in linear programming language, this is called the feasible set of x's. It's the constraint set, capital K in the notes. Right. Okay. So let me draw a picture to show. Or maybe I'll just ask, how many of you are already familiar with linear programming? Oh, quite a lot. Okay, so I won't labor the point, but let me just draw a picture. So my picture will be just here. So that's n equals 3. So this is the x1, x2, x3 space. And x greater or equal to 0 means what? It means that I'm in this 1/8 of the space, right? If the non-negative, well, I would say quadrant, but I really should say octant because it's 1/8 of the full 3D space. So I'm in here, and then maybe I have m as maybe just one constraint, like so let me take the cost to be, say, x1 plus 2x2 plus 5x3, say. And the constraint, I'm just going to have one equation, x1 plus x2. Let me make it easy. Make that constraint an easy one. So this is what we're going to minimize, and that's what we have to satisfy, as well as x greater or equal to 0. So that's a plane. One equation gives us a plane in R3. The plane would go through, would hit the axes at 3, 0, 0. And so the point has to lie on that plane, and it has to lie in the octant, so that plane is chopped off to be a triangle. This is a good visualization of linear programming. And what's the conclusion? Well, our cost is linear. So the result is that one of these three corners is the winner. It could happen. It could happen that maybe I have equal values on those two corners, and therefore all the way along would be also winners. But when I have a linear function, it's a maximum at the ends. And these are the ends, those three corners. So 3, 0, 0, 0, 3, 0, or 0, 0, 3 are the three corners. And one of those is the winner, and the problem is solved. And in fact, for this case, since I'm minimizing, I guess it would be that corner that wins. So let me give it a star, not an X. Yes, 3, 0, 0, because that, no, that's 3. So the value turned out to be 3 at the point 3, 0, 0. And that's X star. Okay. Good. Okay. What more do I want to do? I said yes.
Shouldn't it be the 0.003?
Should it be? So no, 0.003 would have x3 as 3. That's fine. It gives us a chance. I think that would give me a cost of 15. This would give me a cost of 6, and that would give me a cost of 3. Yeah, obviously, if we could enumerate all the corners, we would have a super fast way to get the answer. But the trouble is, of course, that for large values in of m and n, there are exponentially many corners, and we don't want to see them all. So that's what makes linear programming take time and need ideas. So for algorithms, there are two types of algorithms, two types of codes that solve these. The older, well-established ones are so one way is the simplex method, which finds a corner. We know the optimum is one of the corners, so it'll find one corner, and it'll go to the next corner. So if it starts at one of these corners, it will travel along an edge that lowers the cost, and it has to stop at the end because it's linear. The cost will keep going down and going down until it bumps into the end point, and then it can't go further. And then we would, from that next corner, we would go to a next corner. Each time, it's like steepest descent on the edges. We from the first corner, we go the steepest way till we can't go further. We've hit another corner, then we recompute the linear algebra, find which direction is steepest from there, and so that's the idea of the simplex method, which was invented by Danzig. And the algebra is not going to be in today's lecture, but it's straightforward. Well, people have to optimize it because that's a highly frequently used method. Yeah. Okay. But then about 20 years later, maybe, or 30, I remember going to a lecture in downtown Boston by Karmarkar. So I have to put his name down, Karmarkar. And he was in the New York Times, all the newspapers, so it was a big deal. He had an alternative algorithm, and the exact algorithm he proposed hasn't survived until today, but the idea has. And the idea was to travel inside the feasible set and not around the edges. So his idea, because in here, we maybe travel down near that edge, start again, travel again. So it's steepest descent in the constraint set, the feasible set. And you can use calculus and this idea. So this is interior point methods. So I'll just use the word interior. That's telling us that we're inside the feasible set. We don't come all the way to the boundary intentionally because we want room to move and to find derivatives and to use Newton's method to minimize. You choose a search direction, just as all of optimization does. And in that search direction, you track it and you stop before you bump into the edge of the feasible set, and then you compute derivatives again. So you can use calculus. And it's a method that, it's an idea that the interior idea came before Karmarkar, but he got super publicity, so it really got attention, got new thinking, and new ideas came, partly from people at MIT, and these two are now still locked in competition. one hasn't beaten the other in all problems. So linear programming is here, but then for nonlinear programming, quadratic programming, where the cost is quadratic, nonlinear programming, semi-definite programming, that's where you have a matrix unknown and matrix constraints. Those are all, the more complicated you get, the more it tends to be interior point methods. Okay, that's a summary of linear programming. Now I'd like to give an example. And then I haven't told you the main, well, let me tell you the main fact about duality. Okay. This is really, and I'll write that maybe here next to it. So duality is there's a dual LP. And that dual is going to do a maximum instead of a minimum. And the cost is going to involve the B from the primal problem. So this is now called the primal problem, and this is its dual. So they're twin problems. They use the same data, but quite differently. It's like transposing things. So let's call the unknown y. So for y1 to ym, I guess, because b, the right-hand side over here, is m by 1. So that's maximize that subject to what are the constraints? Well, the cost function over here, c, the cost vector, goes into the constraints. And I think the greater or equal sign probably becomes a less or equal to sign. The a gets transposed. I think that's probably the constraint in the dual. And it happens it doesn't need y. We don't have y greater or equal 0 over here. Okay, so that's a dual problem. It has linear cost. It has linear inequality constraints. It can be solved by the simplex method. You could choose whether you solve that one or this one, because if you solve one, you solve the other. The two are closely connected, and that's the key idea of duality. So maybe I'll put the idea of first of all, of weak duality. Which says that this quantity that we're trying to maximize, we're getting it as large as possible, is always less or equal to any C transpose X. This is for any feasible, allowed, any X and Y that satisfy the constraints. Remember, feasible means satisfies the constraint. So, in other words, this problem, this maximization problem, you're trying to push this up. The minimization problem, you're trying to pull this down. And it's easy to show that the B transpose, it's easy to show that inequality. Let's do that. So B transpose Y, proof. Should be a one-line proof. So B transpose Y. Okay, what do I do? So B transpose Y. Well, I look over here. That's where B shows up. That's X transpose A transpose Y. Right? Because B is AX. I'm feasible, so my B is AX. And for any X, this is for any X, that B is going to be AX. So am I good so far? And now what do I do? Well, now I look here. I see A transpose Y sitting right in front of me. So I say, well, okay, less or equal to, and I guess I'm done. A transpose Y is less or equal to C, so I have X transpose C, C transpose X. So So this equals this, less or equal that. I've got it. Weak duality is just put together the requirements on x and y, and you have it. But was this important? You know, if the mathematics is right, everything has to have its place, play its role. And so what's the role of x greater or equal 0 there? Why do we need x if we just even think of n equal 1, just a number? Where do we use the fact that x is greater or equal 0? Do we use it? This looks so smooth because A transpose y, I'll write that as x transpose c for the moment, just so your eye says that same x transpose and the A transpose y is less or equal c. Where is x greater or equal 0 coming in? There's yeah, that's true, but I want to see. So here's my point: that the fact that A transpose y is less or equal c, that's fine, highly important. But if x was negative, it would be the other way. You would get the other way, and you wouldn't have what you want. So we really do use the fact that x is greater or equal 0 to say that I have this less or equal this, and then I multiply by something positive, and then I still have less or equal. Okay, good. So the math is right. Everything does its part. And then, of course, the beautiful result, the important result is that there's strong duality, just called duality, which is that at the maximum. Now, this is not for any x and y, but this is going to be for x, y star, the winner, and x star, the winner, equality holds. So that's duality. The maximum in the dual problem is the same as the minimum in the primal problem. The two have met. There is no duality gap. In some cooked up nonlinear problems, there could be a gap between the maximum and the minimum, but you hope not. And here, the big theorem is not. They're equal. You push this up, push that down. So that's another way to say that duality is that this is, I'm pushing that up. That's I could write that as a maximum of a minimum equaling a minimum of a maximum, if I wanted. So it's the duality in linear programming was the same as von Neumann's minimax theorem, and his theorem applied to two-person games. So the key math result is that is duality for linear programming. And it's going to be, you'll see the same thing happening for two-person games. And it's a minimax theorem or a saddle point, or it's just things come out right. Yeah. Yeah. So just to mention that mathematical programming, of course, includes much more difficult problems. This is linear programming. That problem, as you see, has a beautiful, simple theory, and the paying attention is paying attention to the algorithm, because you've got two important choices, and they both get highly developed. Now, okay, so for game, now I'm going to turn to, I'll do a example of max flow equal min cut to see what and then go to two-person games. So here's an example of a okay. So I start with a graph. Yeah, let me just imagine So this is the source. This is the sink. And I'm sending flow through the network. So it's a network that I'm sending flow through. So my job is to maximize, I'll set x at the source to be 0. And then the flow, the total flow will come into the sink, so I want to maximize x at the sink. So it's a linear programming, and there are constraints. So what are the constraints? Every edge has a capacity. So let's see, suppose that edge has capacity 5. Let me put capacities on all these edges. 2, 1, 3, 4. I'm just stabbing around here. 1,000. And let me say 2 and 4. Okay, I have no idea what's happening here. But if we see the problem, we'll probably be able to solve it. So these constraints are that the flow variable, which would be the y that I'm trying to maximize, cannot, the amount of flow, just in ordinary words, the amount of flow on the edges can't go higher than the capacity. I could send 11 along this edge, but then I've got nowhere to send it after that. I could send, well, 900 on that edge, but obviously it would get stuck there. So the question is, what's the maximum I can send through that network? It's a classical problem. And in fact, it's an integer programming problem. These are all integer capacities. I could insist on integer flows. But it's a very remarkable integer problem because I could allow fractions and the answer would not involve fractions. In other words, if I keep it as an integer problem, then the mathematics is definitely harder for an integer problem. What's different? So the x's could be integers, or they could be real numbers. Over here, they were real numbers. I happened to get an integer for this, but if I had 10 crossing planes in 15 dimensions, the integers would be totally lost. But the point is here that if I allow real numbers, it doesn't get me any more flow. That the winning flow is an integer anyway. So it's an integer problem which can be safely relaxed, and you can safely use simplex method or Karmarkar's method or any interior point method with non-integers, because in the interior here you're not starting or ending at integers. You can do it because the integer answer will be in the end better. Okay, and what is that answer? I think I've made those capacities like too easy to. Oh, I didn't do this one. So what shall I say? Shall I make it large, like 9? I don't know. Okay, what's the best we can do through that network? I can't see it from here yet. What should I do? Obviously, in this simple problem, I can get anything I want pretty much to that far. But then what can I do? Let me even make that 19. Okay, so I'm not imposing much of a limit on that edge either, but these edges are quite tight limits and these are sort of intermediate limits. What do you think is the most I could send through? And how would you show me that I couldn't send more? That's the key question. I want to get a bound on the, an upper bound on this maximum. This maximum getting into the sink is less or equal to, and what number would you propose? Could I get 1,000 through? I could start, but of course it would pile up there. I couldn't get further. What do you think's the best I can do?
10.
10? I can't do more than 10? How could I do 10?
So you go 12,
12 this way?
yeah, 19,
Oh, okay.
and then split the 8 into, can you split? And then,
So I see 10 that way, 10 this. Yeah, absolutely. You can split, and then this could go here, and then it would be able to go there. So I can get 10 through. Correct.
But you can send something
Can I do anything better? Oh, I could be sending some up this way at the same time. So I could get 3 along the top. I could, so this is like an auction. Okay, we can get up to 13. Can we get, so that was 3 going this way and 10 going this way. Is 13, can I not exceed 13?
14. You can send.
Do I hear 14? Yeah. Oh, I've got a lot of room for one more, so okay. So 14 can make it. All right, do I hear 15?
Can you do 2 more on the bottom, like 12 instead of 10? And that's
If I did 12 then, what would I do?
Split the other 2 up.
I'd send 2 up here. Okay, what am I going to do with them from here?
Go all
Send them
the way up again.
up again
And
and along, but then the 3 that I had right now would be cut back to 1. It's a lot of fun, this max flow problem. And I'm looking for a bound to know when to quit, to know when I've optimized. That's the whole idea of duality, is to find some upper thing that I'm trying to push down, and but I can't go beyond it. So I don't think I could get more than, you see, everything has to cross this middle. So 3 and 4, 9, I don't think I could beat 23. If somebody said more than 23, I would be very doubtful, because I couldn't get it across the middle. But then can I get 23? I doubt it. Maybe 14 is best possible. So how would we show that 14 is best possible? I think if I could find, so this is called the cut, a cut in this network. So, oh yeah, I see a cut like there. You see that? Every bit of flow has got to cross that cut. And the total capacity crossing is the 3 and the 1 and the 2 and the 8, which is 14. So I can't get more than 14 through, and somehow that cut is loaded to capacity. Probably those edges all have to be fully up to capacity, and then that cross the cut. So the cut is a separation of edges that go with a source, and nodes that go with a source, nodes that go with a sink. Yeah, and then it's the edges across the cut. So yeah, is that okay for an example? So that's the duality. The maximum flow turned out to be 14, and the minimum cut turned out to be 14, and when those match, 14 equal 14, I know I'm through. I know I'm through, because I'm able to get 14 through, and I could never get more. Yeah, 3 and 4 and 6 and 8. Yeah. Okay. And of course, in a big network, the maximum cut is not going to be visible. Well, you couldn't, it would have thousands of edges. You couldn't see what you were doing, but you could solve this problem fast, actually fast. And it's an important, in practice, it's an important example. A lot of other things fit into the max flow min cut example, and therefore solving it in faster than, I didn't even say about speed. So the simplex method, almost always, it's average case. Dan Spielman, who was on the faculty here, who's just terrific in this area, was maybe among the first to study the average case. So for an average choice of A and B and C, instead of making the worst choice. For the worst choice, you can create a feasible set that it has to go corner, 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 corner until to get to the end, so the simplex method would take exponentially long. But that's extremely rare. It doesn't happen in practice, I think, and the average one is polynomial. So it's a fast method on average. And we can show, actually that was a famous result. It came from Russia, that linear programming is, in the big P versus LP world, linear programming goes with P. Linear programming is a problem that can be solved in polynomial time. The simplex method won't always do it, but it can be done. Yeah, there came into the world ellipsoid methods, and it was an exciting time to decide that linear programming was actually P and not LP. Yeah. Okay. So this is a case of duality where you can understand duality by the statement that the flow can't exceed the capacity of the cut. So that's what duality is. Any flow has to be less or equal to the capacity of any cut. The capacity being the sum of the one. So, of course, there are other cuts. That cut has to be crossed, but that's got 3, 7, 14, 22 capacity. So the 14 capacity was the minimum, and that gave the maximum. Nice, isn't it nice? Yeah. Okay, so there's another world here of two-person games that also has duality and could be expressed. So let me just talk finally today about two-person games. So the two persons are X and Y, of course. What other names could they have? And there's a matrix involved. This is the payoff matrix. So let me take a very simple game first. So X is going to choose one of these rows, and Y is going to choose one of these columns. And let's say payoff from X to Y. I like it that way because then X, who's paying, is going to be minimizing, as X was up here, and Y, who's collecting, is going to be maximizing, as in the dual. So the payoff, well, let's see. I think maybe 1, 4, 2, 8 would be probably a fairly easy game to play. So it's a two-person game, a zero-sum game. Zero-sum means all pay. What X pays goes to Y. Y gets all that X pays. There's no third party here. No lawyers involved. Okay, so and Y is going to choose a column, and X is going to choose a row. And X wants to make it small, and Y wants to make it big. Okay, so what happens in this game? What does Y choose to make it big? The second column. What does X choose to make it small? The first row. So it's going to be focus in on that 2, because if Y keeps choosing that column, 2 is the best, the least that X is going to have to pay 2, and he achieves that by choosing the first row. So it's a simple game. That's a saddle point. It's a minimum for Y in its column, and it's a maximum for X in its row. But of course, another matrix might not have such a saddle point. So do you see okay with this game? That would be a sort of straightforward game where simple strategy, column 2 every time, row 1 every time is the optimal. But now let me just exchange that. So again, X1 and X2, Y1 and Y2 are the 2 columns. What happens now? Well, Y kind of likes the big number 8 there. So goes for the second column, still has the bigger numbers. So Y aims for column 2. But then what does X do? What row does X choose if Y is into column 2? The second. Okay, so have I found a saddle point where Y chooses this column, X chooses this row? Is that a saddle point? No, because what will Y do now? He sees X choosing the second row all the time, and Y sees a 4, a very tempting 4 in that row. So Y is going to choose Y1, the first column, pretty often. Not all the time, because what happens if Y chooses this column all the time, then X will choose this row, and only the payoff will only be 1. So things went downhill for Y there. So this is not a saddle point. And what do? Mixed strategy, which is Y will choose the 2 columns with some probabilities that add to 1. So there'll be a third possibility that px1 and py1, p times this column, and 1 minus p times the second column. So that'll be p plus 1 minus p times 8, and 4p plus 1 minus p times 2. That's this mixed column. By mixing his strategies, we have a strategy like a third person, Y3, and of course the X is going to notice after a while what the strategy is. This is an open competition. You're not hiding. You're not able to hide anything. You might think, well, maybe Y will jump around, but that's foolishness. Y is going to end up finding the best choice of P between 0 and 1. And it will actually be between 0 and 1 because the extreme strategies of column 1 and column 2 were not winners. But now X is going to do the same thing. Px1, he or she is going to combine those rows. So this would be P1 for the first row and P. Oh, I better choose another number. What's another letter than P? Q? Good. Q. Okay, Q. Okay. So this row is a combination of those rows, so it's Q plus 1 minus Q times 4 in the first position, and 8 plus P times 8, and 1 minus P, Q times 8. Q times 8 and 1 minus Q times 2. I'm sorry that I've written this too small, but what's going to happen? What's going to determine P and Q and solve the game? Well, if these are equal, then what happens? Then X is okay with either one. X has nothing to choose if those are equal, and Y is staying with this mixed strategy, which gives him this third combination column, then X is good. Now you might say, well, then X could do what it wanted, but X couldn't do what it wanted. If X doesn't stick with the optimal strategy Q for X, then Y will take advantage. So really the game settles down to once. So these should be equal. So when those are equal, what do I get? I have P. It looks like I have 8 minus 7P there for the first one. And here I have 4P minus 2P. Is 2P plus 1? Did I get that possibly right? 4P minus 2P is the 2P. And, it's 2. Yeah. Okay. So those are equal. And that tells me that 9P is 6 and P is 2/3. So it turned out that the best strategy for Y is 2/3 on the first column, which didn't look so promising, and 1/3 on the second column. And by creating that strategy, what do these numbers come out to be? And they're supposed to come out equal. So 4P plus, so 4 times 2/3 is 8/3, plus 1 minus P is 1/3 times plus 2/3 is 10/3. So I think that this is 10/3. And if that one isn't 10/3, I'm very surprised. So it's 2/3. Help, is it? 4P, 2P, 4/3. Yeah, tell me they're the same. Did I set them equal? Yeah, I set them equal to find P, so they have to be the same, except for instructor mistakes, which never happen, of course. Okay, so those should be equal. Then X has no way to do better. Choose these columns, but he can't choose those rows freely, because Y could take advantage unless. So this would give the best strategy for Q, the best Q for X. Yeah. Do you see that picture? Now there could be it could be a much bigger matrix, of course. There could be other columns. Suppose there was a 0, 0 column. What would be the effect on the optimal strategy of having that additional column, that additional option for Y3? Well, he wouldn't take it. Okay. So let's make it more tempting. 10, 10, 10. Okay. Oh, he would take that, right? Yeah, that was not. So, well, I'm not sure what I'm trying to say here. Yeah. There certainly could be rows that are columns or rows for X that don't enter the mix, the optimal mix strategy. A mixed strategy is some combination of strategies, some combination of pure strategies, like choose this column, choose this row. But some columns may not, or rows may not show up in the best mixture. So I won't complete that partial thought there. Okay. So what do you see that we have a duality theorem? First of all, you could write that as a linear program. The unknown is P for X, for Y. The unknown is Q for X. So actually, just have one unknown in this simple problem, but for this small problem. But you have a minimization, a maximization. They meet at the optimum, and the duality theorem becomes the theorem for two-person games. Linear programming matches two-person games. The point about two persons is very important. Three-person games are incredibly complicated. No theory at this simple level would solve three-person games. So that's where John Nash's Nobel Prize comes into the picture. So his Nobel Prize was in economics because of the wide applications, but he was able to analyze the problem of, and for functions more than for matrices, of three-person or n-person games. So you know the story of John Nash? The book, A Beautiful Mind, and the movie, A Beautiful Mind. So it's one of those movies that involves MIT because he was here. But you can't recognize anything about MIT in the movie. It's like Good Will Hunting. You're maybe in some basement of some remote building, but anyway. It was, of course, a tragic, and then wonderful, and then tragic again for John Nash. He had, so when I met him, he was going to teach linear algebra one section, but that never developed. That was when his mental state was going downhill, and he moved to Princeton and just stayed. And then the wonderful thing was that he improved, and then the very sad thing was his death in a car accident on the way home from the Nobel Prize. So quite a story, an amazing story. Yeah. Okay, so that's specific optimization problems, linear programming and two-person games. And I hope that Friday it will be Professor Swa. Anyway, the lecture will certainly be about stochastic gradient descent. Good, thanks.